So the subject today, chaos, is probably the most important idea of the first part of this quarter. The kind of main phenomenon we're going to look at, right? So the theme here first was, oh, we get to stick our head inside the gray box and see what can go on, how behaviors can change as a function of parameters, and so on. Now I just want to focus in on this complicated so-called chaotic behavior and give a definition of it so we can be a little more precise and start thinking about how to be quantitative about how unpredictable or complicated these solution sets are. So today we're going to start moving in that direction and give no longer using the word chaos in this qualitative sense. We'll give a nice quantitative definition. One of the benefits is we're actually going to be able to look into higher dimensions and kind of imagine all the different kinds of attractors that can happen in an arbitrary dimension once we become more quantitative about this. So we'll end on a classification scheme. Okay, so what is this? I mean, so far we've been talking about these nonlinear systems in terms of, and we've been looking at very complicated trajectories or orbits. They're difficult to follow. I mean, you even think back to the physical demo with a pendulum, right? Extreme behaviors right around the magnet or at large energy, quite predictable, almost periodic. And then there's this intermediate range where the orbits are quite complicated. Also, there's this notion of recurrence. We constantly come back to the same part of the state space, never exactly repeating, because then that would be a periodic orbit, since the equations themselves are deterministic. As soon as you're in one state, the next state is completely determined. So these sort of close paths, but also sort of built in this local divergence. Nearby trajectories are moving apart from each other. And that's going to be a key thing we're going to try to quantify. And the other way where we're talking about it, again, just very qualitatively, was that if we didn't have exact control over the initial condition, think of the pendulum again, downstream, the eventual behavior, which magnet the pendulum bob was attracted to, was hard to forecast or predict. In some sense, all you could do there is give a probabilistic description of which of the four magnets the system was going to go onto, even though, instant by instant, it's a completely deterministic system. So we need to understand how a system makes these complicated behaviors, complicated trajectories. So I'll use the word geometry here. What kind of geometry in the state space produces this? So that's the theme today, is to look at what I'm going to call stretching and folding. There's a very prosaic description of what's going on. These nonlinear differential equations or nonlinear discrete time maps, what they're doing is they're taking state space as if it was a piece of dough and stretching it out and folding it over. So that's what I mean. And I'm going to give a series of examples where we start with sort of the simplest stretch and fold mechanism and then increase the complicatedness of the model so that we can move towards more realistic systems like the pendulum, the Lorenz and Rössler. But the first models will distill the essential aspect of the stretch and fold mechanism and will lead us to a way of thinking quantitatively about how unpredictable a system is. So there's this recurrent instability. So things are stretching out, neighboring trajectories are stretching out, but for this to be an attractor, the solution set to be an attractor, somehow this has to fold back on itself to be a compact object to be attractive. So that's what we need to understand. So the first model, and this really is the 0th level canonical model of a chaotic system, it's called, well, no surprise, the Baker's transformation. So you really should be thinking about state space, DOE. So what I'm going to show you here is a two-dimensional state space. So this is a map of the plane into itself. It takes a point to another point. But let me just introduce it first in terms of how it operates on the whole state space. And I'm coloring things here just to guide the eye. So I'm going to take this unit square and this Baker's map. The first thing it's going to do is stretch it horizontally along the x-axis by a factor of 2. And it's going to shrink vertically by a factor of 2. So half the height, twice the width. The amount of DOE is conserved here. The area is the same. And then what I'm going to do is I'm going to cut. And here's where I'm using the green and yellow colors to guide the eye. I cut right at the halfway point on this wide strip. And then I stack the green half, the right half, above the yellow part, which is the left half. So this is one step. This is what this map is going to do, and then I just do it again. So when I do it again, I start with this cut and stacked piece here, and I do it again. So now I'm going to stretch it by a factor of 2 horizontally, shrink it by a factor of 2 vertically, and then I cut and stack. So again, we're not leaving any dough on the cooking board here. All the area is conserved. But now you sort of notice one thing. I'm starting to get these stripes. So initially, we had 2 stripes. I did it the second time, I had 4 stripes. And if I did it a third time, I'd have 8 stripes. If I did it 10 times, I'd have 1,024 stripes. So just doing this operation 10 times produces a very, it's like phyllo dough, right, or making croissant or something. Layers and layers and layers. Not only that, in the horizontal direction, if I had 2 initial states, because each full iteration of this map, if I had them separated by a little delta, that's going to grow. That'll double each time. So even if I start arbitrarily far apart, some little delta difference, after I've done this 10 times, not only do I have 1,024 2 to the 10 layers, this initially close pair of points will be a factor of 1,024 further apart after just 10 operations. So that's the main idea. Now, it's idealized, and we'll see how it's idealized when I make these maps a little more realistic. So you can ask, is there some prototype system I can do? Yeah?
So if you have 2 points that are vertically aligned, that are very close, are they going to remain close until you hit a certain number of iterations?
That's an excellent question. Right. So it's almost the complementary argument to what I said about 2 nearby horizontal points that just differed horizontally by some epsilon. That's going to double each time. 2 times larger, 4 times larger. If they're exactly vertically separated, because I'm squishing by a factor of 2, any little delta is going to go down by a factor of 2, a factor of a quarter, factor of 8, exponentially fast. So we'll come back to that. Yeah?
So if you have the 2 points and they're getting farther and farther apart horizontally,
yeah,
wouldn't there reach a point where when you cut down the center and stack it,
right,
then they would get stacked, so they wouldn't necessarily be 10 to the 24 points farther away?
Right. Well, if they were 10 to the minus 26 together, then they would still be in the same horizontal line. But you're absolutely right. That unit square has a size. So as soon as that separation gets on the order of 1, those 2 points will now fall into 2 different pieces that are getting stacked. And so the notion of difference, at least the simple argument I'm making, falls apart. Yes? Yes. Right. Okay, so we'd like to study some equation, some dynamical system, explicit equations to study this. So I claim that this pair of equations implements this Baker's map. So in the x direction, I just multiply the x state, the x horizontal component of the 2-dimensional state by 2. I do this mod 1, because I want everything to map back into the unit circle. And then the horizontal direction, I multiply the vertical coordinate by half. And that's going to give me the shrinking by a factor of 2. And then the cutting is done partly with this mod 1 up here, and then also by adding this offset. So when the x-coordinate is greater than a half, it's going to take all of that part, which is now, if you think about it with a graphical picture, the right-hand side of a stretched horizontal slab, and offset it by half. That's essentially stacking it on top. So you should probably step through that argument to convince yourself that the graphics I just did are implemented this way. Okay, well, now we have some equations. We can do a little bit of analysis, despite all my sort of saying, oh, these things are unsolvable. We can ask, for example, what's the Jacobian? Okay, so I can form this matrix of partial derivatives. If I call the x of n plus 1 equation, the right-hand side f, and the y right-hand side g, this would be partial f, partial x, partial f, partial y, and so on. And it's simple. You can just read this off. There's only the x term in the equations. When I take the partial derivative of this with respect to x, I just get the 2 out, and with respect to y, there's nothing. Okay? So I end up with this diagonal matrix. So this upper number here, so this partial f, partial x, that's 2, and then the partial g, partial y is a half, and the others are 0. Okay, we have a matrix. We can do a little linear algebra analysis. The first thing to notice is that this matrix doesn't have any dependence on the current state, x, y. It's constant. Wherever I am in the square, I get, this is the matrix. So that means, locally, whatever the stability, it'll be independent of where I am. It's uniformly the same stability question. So I just calculate out the eigenvalues. Well, okay, we just do this by observation. Here we have a diagonal matrix. We know what the eigenvalues are. They're just on the diagonal. And so we have our largest eigenvalue is 2, and the next one is a half. Lambda 1 here corresponds to stretching horizontally and shrinking. And you can verify the directionality by looking at the associated eigenvector. So the eigenvector associated to eigenvalue 2 is just 1, 0. It's just pointing along the x-axis. And that, for the lambda 2, second eigenvalue being a half, that's purely vertical. So the two eigenvectors are perpendicular. We can look at the determinant. So the determinant is telling us locally how much area is expanding and contracting. And we know that the determinant of a matrix is just the product of the eigenvalues, and we see 2 times a half is 1. So that tells us that this is area preserving, or that I'm not leaving any dough behind on the cooking board as nothing's dissipated in this more physical language, vocabulary. Yeah. And then again, this analysis is all independent of where you are. So every point in the state space has this horizontal stretching by a factor of 2 and vertical shrinking. Everywhere, uniformly. And that's exactly where it's sort of a little too idealized. But okay. Also, because it's area preserving, we don't really have an attractor in the sense of, for the Rissler-Lorenz, the flow was coming down to around the origin and staying in those sets. There's no shrinking here. So we can modify, and so this is the next step to make this Baker's map model more realistic. We can add a little area loss or state space dissipation by adding a parameter. And what I mean graphically is very easy to say. We're going to start with the same unit square, and then what I'm going to do is I'll stretch it out, cut it in half, and then stack. But when I'm shrinking, I'm going to shrink it more than a factor of 2. Say by factor 3, a factor 4. So when I put the dough back in, there'll be space. Okay, and the same thing happens again here. If I apply this again, so now I've done this once to the state space, and I'll do it again. Starting here, I apply the stretch, cut, and stack. Now now the layers are maybe a little more apparent. But now the set of states that you can visit, it's actually shrinking in the vertical direction. Say by a factor of 3. It doesn't exactly map back in. It goes down by a factor of 3, a factor of 9, 27, and so on. It's actually going to shrink in the vertical direction down to nothing. Okay, well, we'll come back to that. Well, how do I modify the previous Baker's map equations to take this into account? I'm just going to add, as you probably guessed, just a coefficient in front of the y-ends here. So before we had a is equal to a half, and that made it area preserving. But otherwise, the equations are the same. So have a stacking here, x less than a half, x greater than a half, the two different treatments of the vertical coordinate, still offsetting by a half. But now I'm controlling how much shrinking I'm getting so that it is a subset at the next time step. Okay, so think of this as a control parameter that ranges from 0. Right? If a was 0, this would just go to a single line and a half, and then we'd have this just stretching horizontally. So that would be just a one-dimensional object. Or when it's a half, that's the previous example where it fills out the full square, so a vary between those two is giving us this kind of phyllo-dough structure. Same stability analysis here, except instead of a half on the diagonal, we now have a. So the calculations are straightforward again. The maximum eigenvalue is still 2. That's stretching in the horizontal direction, but now the shrinking rate is a. Convince yourself of that. That is the eigenvalue on the diagonal there. And then but we still have the same eigenvectors, horizontal and vertical, for the stretching and shrinking. And now we calculate the determinant of the Jacobian, again, to calculate this area preservation, or in this case shrinking, it now depends on A. And so we say that areas are shrinking when A is a half. So if A was a half, then this would be 1, and we preserve areas. When it's less than a half, then this is going to be shrinking every step by some factor. So if it was A was a third, then we'd have only 2/3 of the unit area the first time, 4/9 and so on, keep iterating. So now we can have attractors. We actually have a set that is invariant. Just curious, that's the infinite time set, what's invariant, and then it's being, wherever you start in the square, it's coming down to the set. So let me show you a simulation of this for A equal 0.3. Okay, so again, we have these gaps here now, and if you squint your eye, you see there are sort of 2 bands. Well, clean off your glasses a little bit, and then you see 1, 2, 3, 4 bands. Look a little more closely. Well, there are 8 bands. Even more closely, there are 16 bands, and so on. So now these bands are laying out what we call a fractal or self-similar structure. Right? One way to think about what that means is, again, if I squint my eyes, I see 2 bands, but if I zoom in, I can see 2 bands. If I zoom in here, I see 2 bands. As you zoom in, you keep seeing the same structure. So that's this notion of self-similarity. The set, the sort of asymptotic invariant set, the set of points that you get attracted to, has a self-similar character. If I magnify them up, I see the same thing again. I magnify it and all the way down. So this is a little bit strange. It's a set of points that fills out lines horizontally, so it's at least one-dimensional. But in the vertical direction, areas, these lengths are shrinking exponentially fast, so it goes to a 0-dimensional thing. But it's just not a single line. So what is it? So it brings up this question of how we can start to describe these complicated invariant sets. So virtually all of these chaotic attractors have this sort of phyllodo, self-similar structure. For those that have a very large contraction rate, we may not see it, and that's the case with the Rissler and the Lorentz. And we can think of them as sheets. Okay, and we could do the stability analysis, and again, this is just to emphasize what's the problem.
It stopped.
That's fine. It's independent. I'll try it again. Okay, so again, how do we do stability? We look at some point in the plane here, and we just vary it. Say epsilon in the horizontal direction, delta in the vertical direction. We just plug that into equations and look at how the output state, x1, y1, changes as a function of that. And you can see, again, it's basically just writing out explicitly what that Jacobian analysis was. We see that in the changes in the horizontal direction are a function of epsilon, and they grow as a factor of 2, and then the difference between in the vertical direction is just a times that delta separation vertically. So if you did this repeatedly, separations in the horizontal direction go exponentially with the number of iterations as a function of epsilon. So that initial small separation horizontally grows, and then vertically it shrinks with a. As long as a is less than 1, things will be shrink. Okay, so we have this kind of strange set. It has structure to it, but it's somewhere between a one-dimensional line, and it's certainly not two-dimensional because in the vertical direction, the lines are shrinking to 0 length. So how are we going to think about this? So this brings in the idea of the dimension of a set. So what I want to do to motivate a definition is have us think about sets whose dimension we all can agree on. So here, what we're going to do is look at this yellow square, and the yellow points are the set we're interested in, and that is two-dimensional. Okay? Now, the idea of dimension is what we're going to do is look at that set with a, think of it like a microscope, where we have some resolution epsilon that we can zoom in on the set. And at each stage, we're going to look at how many at a given resolution, how many boxes, coarse-grained boxes, contain pieces of the set. So in this first case, it's just to verify our intuitions about what two-dimension is. So here, if I have this unit square and my measuring instrument, coarse grains with epsilon equal 1/2, I have 4 boxes. If I sort of double the resolution or decrease epsilon by a factor of 2, I now have 4 cells in each direction, and therefore 16 in the whole square. And do it again, down to epsilon is 1/8, I have 8 cells on each side, and therefore 64 in the whole square. So the number of squares is increasing as I zoom in. So if we ask, okay, how many cells do I have as a function of epsilon, you can, and I'm picking, an easy change in epsilon from 1/2 to 1/4, so it fits in the unit square nicely. You can argue that the number of filled cells as a function of the resolution epsilon goes as epsilon to the -2. And that exponent here is going to be our dimension. Right? If, for example, I had started out with a yellow set being a one-dimensional line, I went from 1/2, I have 2 cells. Epsilon is 1/4, I have 4 cells. Epsilon 1/8, I have 8 cells. The number of cells will grow linearly with the number of steps, or it would be, this n of epsilon function would be e to the -1. You can also kind of imagine now, if it were a cube, and you did the same varying resolution counting experiment, then this would be -3. Okay, so this number up here is our candidate for what a dimension is. Now, a classic move, and this is a very common thing to do in dynamical systems, is there's some intuitive definition of what we mean by dimension, and what I do is actually kind of invert that. I'm interested in plugging in a set and doing this box counting at different epsilons. So what I'm going to do is turn this around and sort of make an assumption or ansatz. I'm going to say that the number of boxes that I see at resolution epsilon goes as the measurement resolution epsilon to the minus dimension. Or I just simply take logs of both sides and turn this into a definition of this number up here. So our definition of dimension is, I'm sort of taking limits and then letting epsilon go to 0, and I'm looking at how the number of boxes changes as I vary epsilon. And this dimension is certainly sort of the rate of change of the counts. So here's kind of the direct definition. I look at log of the number of boxes at scale epsilon, normalized by the scale I'm looking at, log of that. And then I just look at the ratio that I get as epsilon goes to 0. I'm kind of throwing, it's a very local notion. In fact, if you develop this more carefully, you have to talk about dimension at a particular point. For most of these chaotic invariant sets, it doesn't matter which point on the set you're in, the dimension will be the same. But it takes even a couple days to develop that idea. So anyway, so here's our definition. In some sense, it's sort of the scaling of this number of filled boxes as a function of resolution. Okay, so let's go back to this example, the dissipated Baker's map, and see if we can make some sense of this definition. Okay, so we've already sort of argued it. After I've done the application of the dissipated Baker's map once, I have 2 bands, 2 stripes, I should say. If I do it twice, I have 4 stripes, and so on. So I end up at the nth application of the map with 2 to the nth stripes, and then they're each of thickness, how much shrinking is going on. Say it could be 1/3 or 1/4 or something like that. That would be the shrinking. That's their size. Okay. So question is, how many boxes do we need to cover the attractor when we're looking at it with resolution epsilon? Okay. So here's the picture to get you oriented. I've set epsilon equal to 1/8 here, and you can see that some boxes, some cells don't have pieces of the set, and some boxes do. I just asked me to count up boxes that do. They get a weight of 1. But we can do this analytically here. So just to make things a little bit easier, I'm going to choose to take epsilon to be some function of the shrinking, because that's sort of determining what the natural cell size is here. So horizontally, so if I'm measuring with this resolution a to the n, that means I've applied the map n times. Horizontally, I'm going to have a to the minus n boxes. So the horizontal direction is always sort of contributing that many boxes. The question is, vertically, how many cells don't have a piece of the set? So we just calculate out this function, n of epsilon. It's the number of strips that we have, and they each contribute that many cells. So we end up with n of epsilon just being, doing the algebra, a over 2 to the minus n. Okay, well, does this make sense? We just argued what the n of epsilon function is. We just plug it into the definition and calculate. Well, in this case, it's designed to be straightforward to explain. So here we just plug in our n of epsilon. That's a over 2 to minus n, we just argued, over log of the resolution. Well, we're taking, at the end step, that resolution to be a to the n. So instead of having epsilon go to 0, the equivalent thing is applying the map n times and letting that go to infinity. That's the same thing as the resolution going to 0. Well, but notice, I have logs of these functions. The n pops out, just cancels out. So I end up with an expression, once I simplify things, where I don't have to take the limit because n just disappears. And I get with 1 plus log of a half over log of a. So that's claim. That is the dimension of the set we're looking at, that set. Okay, so for this particular simulation, I used 0.3, and we plug in here, and we get a dimension of about 1.6. Well, I'm not sure my intuition about dimension is so refined. I would know the difference between 1.7 and 1.4. So is this a good answer? Well, at least it's consistent, and certainly agrees in the extremes, right? So remember, when a goes to a half, we're back to the original area-preserving Baker's map, and that fills out the whole square. And notice that if I put in a equal a half, I have 1 plus 1. So d would be 2 in that case. In the case I just turn off the y-coordinate by setting a equal to 0, this just drops off and I have a dimension of 1. So at least the extremes work, and then the actual number you calculate is a little bit consistent with that. So, and you could play around with watch the set that you get from a simulation as a goes towards a half, and you'll see it gets thicker and thicker and thicker until it finally fills out the whole thing. So this is a reasonable, I would argue, definition of dimension. So, yeah.
So does it make sense to have a larger than 1, where your area blows up? It seems like you're going to get dimensions larger than 2.
Right. So there's some assumptions here that I'm making. So, yes. So, first of all, it does make sense to have a be larger than a half. In some sense, the map is creating area. That's fine. But we keep it on the state space, which is the unit square. It wraps around itself with that mod 1. And you have to do that also in the y-coordinate to have it make sense. Otherwise, it's just going to be a set that gets larger and larger. So we need a compact object. So in that case, what you see is the map, so for the area preserving case, we stretch it exactly and shrink it exactly. So when we cut and stack, it exactly fills the unit square. Now what we're doing is when we stack the two pieces, cut and stack, they overlap each other. So the signature of that is that the distribution of points on the unit square is no longer uniform. And so you can describe what's happening when a goes above a half as in terms of you analyze more the probability distribution on the interval. It's still going to be the case that the points will fill out the square. And so the way we say that, and we'll get into this a little bit, we say that the support of the distribution on the attractor would be two-dimensional, and then there is some structure in the distribution of where the points can be. So, but there's nothing to keep you from changing that a parameter however you like.
Would an interpretation be that that probability distribution is adding some of a third dimension?
It's adding more structure to the attractor. So in this dissipative, right up to the area preserving side, the density of points along in the invariant set is uniform. And that changes when A goes above a half. But we're kind of jumping ahead. So right now we're just talking about what's called the box counting dimension. We need to get into some information theory so we can start talking about the structure and distributions. But that's a couple weeks away. So great question, but we'll have to come back to that, yeah.
Am I supposed to see how these equations extend into 3 dimensions right away?
Oh, okay. So we're getting to the point where you should just start thinking about making your own maps, right? So you can imagine there are maybe 2 different ways to extend the dissipative Baker's map to a volume. One would be that you have, let's say we have x, y, z coordinates. I can have stretching happen on 2 coordinates and shrinking on 1. Or the other way around. I can have stretching on 1 and shrinking in 2. So you should be able to go back to those equations I gave you and add a third z equation, and write out those 2 cases. And then you have to, okay, so now, and this dimension idea becomes even more important because you're getting to higher dimensions, right? Well, maybe in 3 dimensions you can argue which of those 2 cases I just gave can have higher dimensional sets as A, or maybe a new parameter B vary between 0 and a half. Yeah.
In that case, would you have to make it volume preserving?
Right. There would be a version of that is volume, of each of those, in fact, that would be volume preserving, and then with the corresponding A and its new parameter, the dimension would vary. But you can go through the same argument and do the same box counting dimension, and I think probably even do those analytically to get an expression as a function of the those 2 dissipation parameters, A and the new one in 3 dimensions. You can also vary the 2, right? How much was stretched horizontally. You can vary that too, and that'll change it. So you should just play around with these things. Easy to, if you have a question like that, you can write it out. Throw it into the, probably one of those labs has enough code to do that. You could just, and then using that JMOL 3D visualizer, throw it up there and look around at it. Yeah. Okay. Now, the thing about the dissipative Baker's map, well, in any dimension, or the Baker's map, is that there was this kind of clean separation between stretching horizontally and shrinking vertically. That it's almost like the 2 separate systems in a way. At least the x equation doesn't depend on the y equation. So the y coordinate does depend on x, because that's where you cut. But so that's, in some sense, not realistic. So what I'm going to do is introduce another complication. So here's another map. It's called a cat map, or more sophisticated, the toral automorphism. It's a toral automorphism. So what we're going to do is now, I'll give you the model where these directions of shrinking and expansion are no longer orthogonal. So in the state space, things will be kind of mixing, or at least the stretching and shrinking don't align with a given coordinate axis. Okay. So first I'll describe graphically what's going on, and then I'll explain the equations for it. So again, unit square. Then what we're going to do is take this. We're going to keep the origin fixed and take the 1, 1 coordinate and stretch it over so it's 3, 2, like that. And I'm actually going to do this, the first version of this will just be area preserving also. Not quite so obvious here. That's why the calculations will do will be important. Now, what you do, once I've stretched it out like this, I've labeled 4 different pieces and then fit them all back into the square again. So this will also be area preserving. Okay, so and what I'm doing here is I'm doing a mod 1 on the x-coordinate and a mod 1 on the y-coordinate. And that effectively shifts everything back down this way. But this is the way to think about it. It kind of expands out. That's the stretching part. And then my chopping or cutting now is a little more complicated. I mod 1. So the B piece stays here. And this kind of A is over here. C is down here. And D is right there. So I have to stare at it a little bit. But right, so the origin stays at the origin. 1, 1 goes up to 3, 2. And then these 2 points here, then these 2 points. And then push it back into the unit square. So here is the mapping for it. It's not too complicated. It's just just this matrix, 2, 1, 1, 1. I just multiply that matrix times the two-dimensional state, calculate it out, and then mod 1 of both coordinates. That gives me the new x n plus 1, y n plus 1. It's clear that the origin is a fixed point, that makes 0. Okay. Now, this stability analysis is more, doing the calculations is more important. So we've got this, well, it's easy to figure out what the Jacobian is. It's just that matrix. Right? The matrix of partial derivatives just is that matrix. So relatively straightforward then to calculate the eigenvalues, which I've done for you here. So the largest one is 3 plus square root 5 over 2. And the smaller one is 3 minus square root of 5 over 2. Notice that the lambda 1, the larger one, is larger than 1, so that will be a stretching direction. And then the lambda 2 is less than 1, and that will be shrinking. But now the eigenvectors play a more important role. It's like, what direction are we doing these? So again, you can calculate that out. And I can just sort of show you here on the original graphic where V1 more or less aligns along the stretching, what we guess is the stretching direction out to 3, 2. It's not quite that. And then this V2 is orthogonal to that. The determinant will tell us whether it's shrinking volumes or not. Well, if you actually multiply these out, lo and behold, it turns out to be 1. So it's an area preserving map. So we're not losing any dough. Also, this Jacobian matrix of partials doesn't have any x or y dependence. So this same stretching, the degree of stretching and shrinking, and the directions are uniform for every point in the unit square. Which is, again, that's the next thing we'll do. We'll relax that. But first, what I want to do is demonstrate a little more graphically how the stretching and folding mechanism works. So what I have here, let's see, can I do this? Let me just check. Oh yeah, okay, good. Okay, and you're not giving me a control. Sorry. Okay, so I'll have to explain the way this movie is going to play beforehand. Usually I have some control over this with the, I'm not quite sure why I'm missing that. But anyway, so what you're going to see is a picture, an artist's rendering of Poincaré. And what I'm going to do is, right, so a picture of Poincaré digitized is a raster image, which means that there are a set of square array of pixels, and every pixel has a color, RGB. So what I'm going to do is apply the cat map to the location of each pixel. But the pixels will carry along, so those will be our states, and they'll carry along the color. The net effect, as you kind of already saw, as I do this, we can kind of get a visual sense of how it's stretching because we can recognize Poincaré. And you'll be able to see the stretching direction and a contracting direction. So anything else I should show you? It kind of goes by a little bit quickly if I can't stop and start things. Yeah, so let me just start that up again. Okay. Now this is discrete. Okay, there. You're going to notice a little kind of beat. So what I'm doing is that's a discrete time map, and I'm doing an interpolation between those. So you can kind of see. Well, okay, first point is that it only took 3 or 4 iterations before it just completely disappeared. So let me go back and start it over again. I wish I could stop it. Okay, so the image, and then you'll see it stretching this way and shrinking that way. And this is only 3 or 4 iterations in. Poincaré is completely lost. The pixels have been mixed so much by the stretching and folding back, it's just lost. This kind of gray-green mass is there. So that just shows you, when I keep talking about this exponential separation of things. Oh, what's going on here? Some structure came back. But then it gets mixed up again. So the first impression is these iterated mappings completely destroy the structure. Now, the recurrence of what are essentially ghosts of Poincare have to do with the fact that the Jacobian is independent of position, just stretching. So there's like 2 copies of Poincare horizontally, 3 vertically there. We're going to go exactly 240 iterations in this. I think this one is halfway through 120. So there he is. He's come back again. So it's a little bit odd. And the kind of interesting and oddness of it has to do with this simplicity of the cat map having the Jacobian be position independent. And there are different order resonances, recurrences, if you will, of Poincare. And it has to do with sublattices of the pixels having different recurrence times. So if all the odd pixels come back in the same relative orientation after 120 iterations, just see a little ghost of Poincare. The most important point is that very quickly all the structure is lost. So that's the main thing these chaotic systems are doing. And then there are special cases like this where you have this recurrence of structure, which is not typical, but fun. So, so he's back. All right, so in principle, see, the mathematics would tell you, oh, it's just going to stretch forever and this will be constantly mixed. But in fact, when you do it on a finite lattice, it's really integer arithmetic, and it turns out that these chaotic mappings are essentially a kind of random but fixed permutation. You do that enough times, the things will recur. So in fact, there's sort of a physics kind of nerdy joke behind all of this. There was a very serious debate back in the late 19th century, early 20th century about Boltzmann's theory of gases and how you could actually average over states. And so there was this idea that, oh, maybe chaotic systems are producing enough mixing that it's okay to interpret the microscopic behavior as if it was random. But then Poincare kind of jumped in and said, oh no, there are these recurrence times. Therefore, there truly is no order coming back. But it turned out once they calculated out the recurrence times for a box of gas, this was many universe lifetimes. So anyway, so that's that. Okay, so now for a little dose of reality. This is going to be the Henon map, which is in that bifurcation diagram lab, the last one, 2-dimensional map. And this is, I will argue, sort of presented as being more realistic. In other words, if I just gave you a set of differential equations or plucked a 2-dimensional map out of the air, this is going to be a little more typical. So it's going to do a similar type of stretching and folding. This one, what it does is, and I have, so let's focus on this unit square here, and I've added the blue and orange arrows and orientations just to track what's going on. So basically what the Henon map does, and I'll just give it to you. Again, it's a little hard to look at these unless there's something like the dissipated-Baker map. Maybe a little hard to figure out what the actual transformation is. Typically, I just try it on a couple of different points, map lines around to get some sense. And then there are 2 parameters here. So we have, so the x-coordinate depends on the y-coordinate and then 1 minus ax squared. So a is a control parameter. And then the y-coordinate here is just b times xn. Pictorially, what it does, it takes this unit square, and I'm not putting units here yet, we'll get to that. But it's basically just taking this unit square around the origin, so it lifts it out of the plane, stretches it, folds it into a horseshoe, and then kind of turns it over and maps it back down around the origin. So notice where these arrows go, like that. Now, as I'm doing this, I'm actually changing the orientation of the set. Notice also that the image of this square, of all this set, doesn't fall in the original set. There'll be some points here, around here, that actually are going to march off to infinity. And there's some areas that are just sort of thrown out. So the question is, where, if we look at one step, there might be an invariant set somewhere in here. Inside this, the intersection of the original set and the image of that set. So what does that look like? Well, first let's do a little analysis. You can calculate the Jacobian. Now, so maybe a little clearer why I kept emphasizing for the previous examples, position independence. Now, the Jacobian does depend on the x-coordinate of the current state, where you are horizontally. So whether things are stable or unstable, whether it's area preserving or not, could be state dependent. But we just have relatively simple again. So minus 2ax, 1 here because there's just that linear dependence on y. B shows up here due to the y n plus 1 equation, coefficient of xn, and there's no y dependence on y. Now we calculate the determinant. Well, that's just the product of the diagonals minus product of the off diagonals. We just have a minus b here. So b in the equation controls the amount of area shrinking, and it's constant, doesn't depend on the position. It just happens. And that minus sign is what I was talking about before. If you actually look at what the mapping does, it actually twists the set around. If you had n orientation, it's going to flip that. So it's b less than 1, areas are shrinking, and then those areas are being flipped over each time. The orientation is being reversed. We can't appeal to analytical ways of calculating fractal mention here because of the state dependence. It really depends on what the orbit is. So one good thing to do is just simulate it. So this is what you get. So now here's some coordinates. So plus or minus 1.5 horizontally, and then plus or minus 1/2 vertically. So it's centered about the origin. And you can kind of see that original horseshoe action. Locally, it looks like a line, but then up here it looks kind of thick, and you can kind of convince yourself that it might have that sort of layered, self-similar structure to it. Well, that's pretty easy to study. You can do that numerically. So here are a series of steps where we zoom in. So here's the original attractor, and then I'm just going to focus on a little square like this to zoom in. So take that and blow it up to this next big square. So out here, at the largest scale, I see, verbally, a thick line and 2 thin lines. And then when I blow it up, around here, what looked like a thick line, that breaks into a thick line and 2 thin lines. I'm saying this thinking we're squinting. And then I can blow this up, and I see the same thing. Sort of a thick line and 2 thin lines. And then, of course, this quote, thick line is composed of a thick line and 2 thin lines all the way down. So you just keep zooming in and zooming in. Now, of course, if you do this numerically, part of the state space you're looking at gets smaller and smaller and smaller, exponentially smaller. So for me to get points in here, I have to iterate many millions of times to find a point that will actually fall into this particular small part of the state space. But you can do this. Computing issues aside, you can just zoom in on these sets that way and see that they're self-similar. Not uniformly so. Right? There's some parts that are turning around and so on, so it's a little more complicated. Okay, so what we did is focus in on kind of a very simple characterization of what's going on, so underlying chaos. What's the fundamental mechanism? And the claim is it's this exponential separation and exponential shrinking, and then somehow the stretching and shrinking happens so that the set maps back onto itself. So we have the possibility of having an attractor somewhere. So it could be a stable invariant set that within it has this constant exponential amplification. Small variations. All done with maps because it's easier for me to explain graphically what's going on. Now you can also ask, well, how does this work in differential equations, the one we've been looking at? So I tend to switch back and forth again between discrete time maps. Some of them are easier to illustrate certain ideas. And then the flows. Continuous time flows are nice because it's more geometry of the vector field, the flow field. But we can make a connection here. So this will get back to maybe give a better explanation of the stretching and folding mechanism in the Rössler. Remember from the 3D simulation demo, it's very flat in the plane here, and then goes unstable in the Z, comes back down. But we'd like to understand a little more precisely what's going on. So there's some type of rubber sheet geometry where, as it's going in the XY plane, things are separating apart, and then it goes unstable, stretching, and then maps back down to itself. So suturing the 2 different pieces somewhere along here. Okay, so let me say that with a series of pictures. So what I'm going to do is imagine I cut this and stretch it out. Kind of start-finish line that we use when we're talking about the return map. So basically what's going on is we have this rubber sheet. This is sort of, you might think of this as the local view. If you were in the attractor itself, what you would see is everything just moving away from you. You can't look outside. You don't see that you're embedded in 3 dimensions. You're in this pseudo 2-dimensional thing, and everything's just kind of moving away. So if A and B, the outside edges of that band, are a unit apart, sort of one time around, that would be stretched to 2 units wide. And then what I do is I fold the sheet back up and identify the B ends, B prime and B double prime, together, folded this way. So that's the suturing part, and then to make it compact, I stretch it around and then identify all the B's at the same point, and then identify A and A prime. So that's kind of that's a first approximation of what this rubber sheet geometry is. Again, you can go into that lab, put in the Rissler equation, and use the 3D viewer to zoom in to where this suturing happens to convince yourself that this topological description is a good approximation. I say an approximation, it's not quite right. Turns out that B and B prime are actually offset a little bit in the actual Rissler attractor, so you should go look for that. Figure out where this is just an approximation. Okay, so now there's another way we can look at the stretching and folding, and now I want to show you some simulation demos. Just describe, maybe this will be a little bit of an introduction to how we're going to do this measuring how unpredictable systems are. And then I'll just stop there for today. So how are we going to quantify this instability? Well, in some ways, the formal mathematics is not so different from what we did with the argument for fractal dimension, the box counting dimension. But here's the basic geometric picture. So we have some initial condition here, call it x0, some dimensional state space. Think of the Rissler-Lorentz, the dot spreading experiments. And we have this reference or fiducial trajectory. Okay, well enough. And what we're interested in is how small perturbations from this, how nearby states evolve. So the idea is, which the dot spreading experiments motivate, is that even if I start with a very small separation, that separation will grow in time. Okay. And I can make a model of that. I'm going to assume that this length of this displacement vector is going to be grow at some exponential rate. So I'm modeling this in a sense with e to the lambda times t. Right? So that the length of the separation vector at some later time grows exponentially as a function of the original size. So this is our ansatz, our assumption. And what we're interested in actually is that exponent, just like we were interested in dimension before. So I'm going to kind of turn this assumption around and start thinking about how I can monitor the growth of these perturbation vectors from an original separation. So again, just doing the algebra, taking some logs and stuff, we see that this growth rate, lambda, is the time average, 1 over t, times the log of the ratio of the initial separation size to the final one. Okay. So this is called, I'll turn it into a real definition here, this is called the Lyapunov characteristic exponent. It's actually introduced by the Russian mathematician Lyapunov in the 1920s or so. So here's the real definition. So we're averaging over time log of 1 over t times log, I use base 2, you'll see why in a second, the logarithm of this ratio of these lengths. So very simple. We have this picture that we start very close and things separate out. Now there are issues, I can't let t go too long because then I reach the size of the attractor. So what I do is, my little calculus thing, I let my little epsilon separation here go to 0 and then I take the infinite time limit. In a sense, it's kind of a local measure of separation. Now, when you do this, in fact, the definition I'm using here, there are a couple different definitions. This definition is close to something you could imagine coding up. Right? If I have a simulator, you could do the dot spreading experiment. Well, this is just for 2 dots. And just kind of on that, kind of, as you're following one trajectory, make little perturbations and see how much they grow and average that growth rate by taking the log of the ratio. these are, in an n-dimensional system, this displacement is a vector. But what happens is that this vector aligns with the most unstable direction. Or the way to think about that is if there's any contracting direction, any component of this displacement vector in that is going to shrink. So that will go away, and what's going to be left will be a vector pointing in the most unstable direction. So this is called the maximum Lyapunov characteristic exponent. And it is the sort of average rate of growth of these small variations. So let's think about what this means. I'm kind of being just a little more precise the way I've described some things before. Imagine we have some measurement resolution epsilon. This will be the size of those little displacement vectors. And I'm going to measure how much we know about the location. It's the log of that resolution, log base 2. So minus log base 2, this resolution will give us the amount of information we have. So allow me to use the term information informally here. If I was measuring the position of the state to 1 part in 1,000, then I'd have about 10 bits of information. We'll come back and actually define what that means and make a connection when we introduce information theory. But this is, it's like a decibel scale for measured resolution, a logarithmic scale for resolution. And now we have some system that is amplifying things at some rate. So the way we're going to think about that is it's actually throwing information away. I've very precisely specified my system, but now all those small variations I didn't have control over, that's being spread out, so I'm losing information. I don't know where the system is. I have to measure it again to recover it. So we have this information loss rate, lambda, or the growth rate of these small errors, and we can kind of cobble together a quantitative estimate of the average amount of time until I can't predict the system. And this is just basic. I'm just saying, with some simple expressions here, what we saw in the dot spreading experiment. I know where it is, 5 cycles around, 10 cycles around. It could be anywhere on the attractor. So, and as a first approximation to that time of unpredictability, it's just the initial information divided by the rate of loss of information. And that gives you a time scale back out. Right. This is units of information, this rate of loss of information per time, toss back up to the top. So if the loss rate, the simple case, like the Baker's transformation, if lambda was 1, every second or every iteration or cycle, I lose 1 bit of information. My measurement resolution, the information I get from that, I lose 1 bit of that. And then I'm measuring to 1 part in 1,000, then that gives me about 10 bits of information, and therefore if I'm losing 1 bit per second, it's only 10 seconds later that I can't determine where the state is. Simple enough. Now, that's probably intuitive given what we've talked about to get here, but now imagine that I convince my NSF program manager to give me like a huge expensive instrument that is 1,000,000 times more accurate, or say 1,000 times more accurate. So in other words, my epsilon goes from 10 to the minus 3 to 1 part in a million. Okay? How much longer can I predict the system? Well, just go through the formula here. I get 20 bits of information about the local state, and I'm losing 1 bit per second. My time of unpredictability is only doubled. So I have 1,000 times more accurate instrument, but I can only predict the system in another 10 seconds. So that's sort of the power of this exponential separation. Basically, at any scale of uncertainty, it's going to be amplified up to macroscopic scale and determine, force you to measure again, because you've lost information. Okay, well, we'll stop there. And then next lecture on Tuesday, I'll talk about how to generalize this idea of the largest Lyapunov exponent measures instability to also capture stability, and that will lead this classifications team, give us some average sense of what chaos looks like in arbitrary dimensions. So, questions? Yeah.
I mean, kind of going back to the idea earlier, but like, it seems like we're kind of modular nature of these attractors almost puts a limit on your uncertainty, like a maximum.
Right, right. Yeah, I mean, there are different questions of what you would want to predict. And maybe you don't really mind that the long-term behavior is a little bit chaotic. In fact, it turns out our heartbeats are not regular, and that is for a very good physiological reason, because our physiology can adapt to uncertain circumstances. It turns out if it's exactly periodic, you're having a heart attack. So this is not good, right? So, but now you don't want the heartbeat to be completely irregular and doing all this strange stuff. It's got to be, in some part of, think of the state space of the heart. There's probably some physiologically useful region where it's regularly pumping blood, but you don't care on the micro scale that it's a little bit unstable. It might even be helpful, but if you were designing the heart in the vector field for this semi-stable, maybe a little bit chaotic oscillation, you want it mostly be stable. You wouldn't want it to freak out and go off to infinity, because then you would die. So there's, from a large scale, there can be predictability. It's all going down to some invariant set around the origin. That may be good, and maybe engineering a system, and that's good enough, right? So there are different levels you can ask these questions of predictability at. And the spectrum of Lyapunov exponents we'll talk about next time will let you capture that even larger scale notion of predictability, how stable these things are. So. Okay, good. So we will see you on Tuesday. And again, don't hesitate to ask us how to get through the homeworks and SAGE and Campy and all that sort of thing. So. Great. Okay. So we have a few things to finish up from last lecture. Remember, last lecture we were trying to delve down into this stretch and fold mechanism, trying to understand how it is that systems can recurrently produce instability. So we went through that in a number of different examples, different maps and flows, with sort of the final, maybe key demo of the dot spreading. That's sort of the paradigm you should have in mind, what these flows are doing, or what even the discrete time maps are doing. Like initially close, initial conditions get spread out exponentially fast, right? So you're an experimentalist, you prepare the system in what you think is a known state, and because of the very structure of the flows, the built-in nonlinearities, take that initially precise information and amplify fluctuations that you had no control over, until finally the initially close states could be anywhere on the attractor, and you've lost the ability to predict. So we ended last lecture talking about a way to quantify that. And it's not really so different from the way we looked at it visually, and this was using the Lyapunov characteristic exponent. So we took two initially close trajectories and states, and then followed them along their trajectory. There's a small separation, and we simply monitored how that small separation grew in time. We made this exponential growth model of that, and turned that around to define what was the maximal Lyapunov exponent. So again, the idea is we have some sort of trajectory flowing around in our invariant set, and then as we're following the trajectory at each moment in time, we're sort of looking very, very close and looking at how small separations grow. So last time we only talked about 2 points separated by some distance vector. And I argued that, well, if there were directions in that separation where there was contraction of state space, then those would shrink. And then this arrow would actually align with the most unstable direction. And then the rate of growth of that along that unstable direction would be this measure of exponential growth of instability. So maximal Lyapunov exponent. And the way to kind of solidify our intuitions about that, we talked about a way of actually measuring. Now that we have this number lambda, the maximal Lyapunov exponent, it gives us the exponential rate of losing information about the initial condition. We can turn that into an estimate of the average time a system becomes unpredictable. If we measure the state within some accuracy, we think of the Lyapunov exponent as the rate of loss of accuracy per unit time. So I went through the example. If you can measure the state to 1 part in 1,000, and the Lyapunov exponent had an amplification of a factor of 2 loss every second, then it would be only 10 seconds until could not predict the system. I pointed out that if we got a much more expensive instrument that was 1,000 times more accurate, could measure the state to 1 part in a million, that only doubled our time, the prediction horizon, from 10 seconds to 20 seconds. So it's a multiplicative factor increase, or an exponential factor in the size of your grants you need to buy the good, expensive instruments, leads to only a linear increase in the time to unpredictability. So that's sort of, in some sense, the power of this constant exponential growth. It's hard to overcome that. So what I want to do today is finish up this discussion of chaotic behavior and how we measure it, and this, in some sense, is amortizing all the work we put in so far. So, in particular, what we're going to do is start to expand this notion of measuring stability to how we also measure instability and stability together, and then we'll come up with a way of going from these various measures to estimate dissipation rate, information production rate, even the fractal dimension. We'll end with a classification scheme that gives us a little hint of what chaos looks like in higher dimensions than we can visualize, more than 3 dimensions. And then I'll actually give you the proper definition of chaos. So kind of clean things up in terms of our understanding the ways we analyze chaotic behavior. Okay, so the main idea here is very similar to the maximal Lyapunov exponent. So now think in some n-dimensional dynamical systems. Lorenz and Russell are 3-dimensional dynamical systems. And we're going to start with the same picture. We have some trajectory that's moving around on an attractor. So we have this reference trajectory. And then instead of, like we did before, looking at a single displacement, 2 initial conditions with some separation, I want you to imagine that there's an n-dimensional basis attached to it, attached to this fiducial trajectory. And it gets carried along. So at each moment in time, we can look at how those basis vectors, normalized initially, how they stretch, how they rotate. And that's going to be the basis of measuring instability and stability. So this is called the spectrum of Lyapunov characteristic exponents. And the definition doesn't look so different notationally, but it's really trying to describe having this little orthonormal basis attached and gets carried along. I mean, if you jumped ahead a little bit, and we'll be more precise later on with some examples, the goal here is really just to look at the local stretching and shrinking. And you think, oh, well, if I had the equations of motion, I could write down the Jacobian, and I should be able to do this. So there's another formulation of this that's essentially equivalent that does that, when you have the equations of motion. What I'm going to talk about here is this more geometric way of thinking about the basis vectors rotating and stretching and shrinking, that in principle you could use, say, on data if you didn't know what the equations were. So let's just stay with this kind of geometric view. So fiducial trajectory, we start at some moment in time with these small separation vectors. So you can imagine there are 3 neighboring initial conditions. But let's just now talk about the evolution of the deviation vector. And then over time, this, in the general case, this basis is going to rotate as it moves through the state space. And then some of the basis vectors will grow in length, and some might shrink. And in fact, along the trajectory, there will always be one that kind of lies along the trajectory, and on average, it doesn't shrink or grow because of this recurrence. I'll come back to that. Okay, so anyway, so that's the picture. So definition, Lyapunov characteristic exponent spectrum. If we have an n-dimensional dynamical system, there'll be these n directions that we can stretch and shrink in, and therefore there'll be n rates. We're going to do an ordering so that lambda 1 is the largest, but it's kind of arbitrary, down to the smallest. And then I'm going to define the ith characteristic exponent to be the exponential growth rate of the initial separation distance for that vector. So I'm starting in a particular direction and letting this thing rotate out, but I'm really just interested in its length and how the lengths have grown or shrunk. So it's the same definition, and then we do a time average. So again, we're looking locally, so in this definition, we let these separation vectors go to 0 in principle, and then we do a time average of them. Okay, and then again, so this is just saying we have some orthonormal basis. A crude way to implement this as an algorithm would be you'd start off with these little vectors, you'd have to choose some period of time, some number of steps of your integration method, you'd stop, do this measurement of change of length, and then re-orthonormalize the basis and let it go again. So as an algorithm, there might be some estimation parameters you have to add, but the idea is fairly clear. It's just a basis rotating along. We're going to ignore the rotation aspect. It's an interesting question. People have tried to develop complex Lyapunov characteristic exponents, equal to the average rate of rotation. But we won't get into that. We're just going to follow the stretching and shrinking of these basis vectors. Now, why do we want to do this? Well, it's clear we're picking up more information than just looking at one Lyapunov exponent. Although if we were interested in just a simple demonstration that a system was unpredictable, then we could just look at the maximal one and not do all of this. But there's a lot we can get from the full spectrum. So in a way, what's happening is we have this trajectory. It's winding around the attractor, and we're kind of sampling the local stabilities and instabilities. And then we get this kind of average, these average quantities back out. So why do we want to do this? Well, here's one reason. It gives us a kind of formal way of thinking about what's going on in the state space. If we were in the frame of this fiducial trajectory, then sort of nearby, we can think of the state space as splitting into directions of exponential separation from us. Those will correspond to positive Lyapunov exponents. And then there'll be other directions where perturbations are exponentially converging to us, and that's going to be associated with negative Lyapunov exponents. Simple enough. So, in fact, there are various rigorous results that establish this sort of mapping between negative exponents and the kind of stable manifold along a trajectory, and positive exponents being associated with the unstable manifold. So this is the connection between this sort of average quantities and this organization of the state space. Yeah, Chris?
Just a quick question. So is there some analogy between the Lyapunov exponents and eigenvalues of the matrix?
Yes, yes. I won't develop that here. Maybe I'll put up a reference, or that might be in some of the reading. Right, there's another way to calculate this when you have equations of motion. Right, and this goes back to calculating the Jacobian and then evaluating the Jacobian along the trajectory, x of t. And you do this each time if the Jacobian depends on the state, then you have to do this. Then you have the Jacobian, and then what you do is, it's actually the eigenvalues of the symmetric part of the Jacobian. So maybe we can come back to that. I mean, that would be sort of a sidebar.
Okay.
At this point, I just want us to think about kind of the motivations and how we're going to interpret these things, because this is going to actually lead to our classification system. This one-to-one correspondence between negative exponents, positive exponents, corresponding to this kind of formal picture of, this kind of canonical picture of nearby things are spreading out and contracting. So sometimes you'll read in the literature, this is called the hyperbolic structure. And it's very much, it goes back to the simplest example, at least the kind of the picture is like the fixed point, like a hyperbolic fixed point, where you had stable manifold, unstable manifold. Now the idea is that's happening locally. You can ask questions like, well, okay, if I have this unstable direction, unstable manifold, what does that correspond to on the attractor? Well, the short answer is pretty simple. The things we've been looking at, if I say, oh, here is the Lorentz attractor, or here is the Rössler attractor, what we're looking at is called the global unstable manifold. That's the subspace in which everything is spreading out. So and I use the word global because this picture and the Lyapunov exponents are defined as a local average over time. They're useful numbers because the trajectory winds over the whole attractor and samples all the states in the attractor, so it's a good average. But this picture here is a little bit, again, it's just kind of a local picture. But the state space is always kind of splitting into these two subspaces. Yeah.
So Jake, here, just on that eigenvector analogy, but in this case, our directions that we're measuring for the line are essentially arbitrary, or at least where we start. Is that true? Or?
Correct. So So you have to make some choice. Exactly what is the orientation of this? So what the kind of mathematics behind it shows that it's if you're on a single invariant set, then it doesn't matter. The vectors will eventually line up in the right direction. So that was why I was kind of hinting at, if I choose one basis vector, then I just look at its length and let it kind of move around. Any orthogonal directions contract, and any component it has an orthogonal direction of contraction will just exponentially collapse. So in a sense, and you can see that if you make a little simulation, no matter which angle you start with, it'll line up right to be within that unstable manifold. So this positive, the direction of instability, which would be associated with the positive Lyapunov exponent, will always lie inside the attractor. So now this is good, right? We have these numbers, and there are a number of things we can extract from the spectrum of Lyapunov exponents. It's not everything, it's just a set of n numbers, right? I mean, one of the things you can't get out of this is the difference between the topological differences, right? The Lorentz has 2 holes, the Rössler has 1. But that's an interesting question, but we're not going to, can't get to that from the Lyapunov exponents, but we can get some distance. So for example, we can calculate the average shrinking of the state space, or what I call the dissipation rate. So we're mostly looking at these systems like the Lorentz and Rössler where state space volumes are shrinking. I already kind of argued before, kind of recapping Lorentz's 63 paper, that he calculated the divergence of a vector field. In his case, for his equation, it turned out it didn't depend on the state, so he just had this whole volume shrinking down. But we can get this directly from the spectrum of Lyapunov exponents the following way. So remember, the divergence of this vector field is just the sum of the partial derivatives, partial f, partial x, partial y, partial z. It's really just the trace of the Jacobian. Okay, so it's the diagonal in the Jacobian, the first partials. Okay, and then I could do a time average of this. In Lorenz's case, it didn't depend on time, so this came out, we had a constant rate of volume decrease. And you can show that you sum up all the exponents, 1 to n, that is this dissipation rate. Sort of makes sense. We're looking at the, locally, along a trajectory, the sampling of the whole attractor, we're looking at the amount of exponential separation, stretching, and shrinking. And if it's an attractor, somehow the net shrinking directions have to overcome any net stretching or separation. So this is going to be a quick way. First thing you can do is figure out this dissipation rate. Again, that's the hypervolume contraction rate, exponential rate. These each take a little while to develop, so I'll just kind of give you the definitions, mostly just to motivate why we think about the spectrum of Lyapunov exponents. We talked in the case of the dissipated Baker's map, this concept of fractional dimension, fractal dimension sometimes called. You can get that also from the spectrum of Lyapunov exponents. How philo-doish the invariant set is. It's a little more complicated expression. So the dimension of the attractor is there's an integer component and a fractional component. So the integer component, it's basically related to the number of positive exponents, except there's a twist, and it comes this way. What I do is I have the whole spectrum of exponents, 1 to n, and I start adding them up. 1 added to 2 added to 3. I sum them up, and as soon as it turns negative, at that I back off 1. That's going to be my integer component of the dimension, j. So start summing them up. If it's chaotic, first one will be positive, next one might be positive, then a 0, then a negative, then a really negative one. That compensates and makes the sum up to that point suddenly turn negative. You stop there, and that's going to be this integer component. And then the fractional component is just how close to 0 that sum was just before it went negative over the next exponent. There's kind of a competition between this will now be negative, the next exponent, j plus 1, will be slightly negative. And so that gives you the fractional component. So there's a certain number of directions that are stretching. That's being compensated, it's an attractor, by some amount of shrinking. And the fractional component is just the kind of net competition between the positive directions and this next negative shrinking factor. Okay. So that little proviso here, this has been used for many, many years, but it's still a bit of an open question how generally it applies. But that's a first cut, it's not so bad. Finally, and this is mostly trying to set us up for what we're going to be doing very soon, is thinking about chaotic dynamical systems as information generators. So we're going to be moving pretty soon, maybe 2 weeks, into information theory. And there's a notion of a dynamical system as an information generator. It's different from the Lyapunov exponents, but there's a relationship. So it's called the entropy of a chaotic attractor. It's noted h mu. More technically, it's called the Kolmogorov-Sinai entropy, introduced in the late 50s. And that, the sort of net information production rate, and the units here are bits per second, is just the sum of the positive exponents. So this will we'll make a more direct connection back to this concept of dynamical system, producing information. This is actually, as we'll see, is actually a global measure of how the state space gets picked up, stretched, and folded, and put back into itself. What's interesting about this result is that we're averaging, summing up these locally averaged quantities. Okay. So now, so now we have the spectrum, and there are these quantities, dissipation rate, fractal dimension, information production rate that we can immediately pull out of that gives various interpretations of how chaotic a system is, or whether it's chaotic or not. There are also some constraints that we know ahead of time that let us get a picture of what arbitrary dimension attractors can do. Okay, so talk about building up to this classification. Okay, so we're going to talk about attractors. So first of all, we're going to have the signature here, the n Lyapunov exponents ordered this way. Lambda 1's the largest, lambda 2 the next. So if we're interested in attractors, we know the dissipation rate has to be negative. Volumes have to be shrinking. Okay, and that's a constraint on the sum of all the exponents. That sum has to be negative because that's what d was. So the net result is at least one in the signature, at least one Lyapunov exponent's got to be negative. And if we only have one, it had better be large enough negative that it compensates any other positive ones because the net volume has to contract. This also means that the dissipation rate has to be larger than the sum of positive exponent or entropy rate. So what we're trying to do is characterize the constraints on these numbers, Lyapunov exponents, and see if we can't come up with a classification. Also, in addition, if the invariant set that we've got the Lyapunov exponents for is not a fixed point, then the flow along the trajectory, think about a little difference vector, asymptotically doesn't grow or shrink. And one way to think about that is that, imagine on the limit cycle, I have a little displacement vector that's tangent to the trajectory in the direction of the flow. It's going to come back to itself, and it better be the same size. So it can't either get ahead of itself or get behind. Otherwise, of course, it was getting ahead of itself, it would go off to infinity. Or if when I came back, it got smaller and smaller and smaller, I'd have a fixed point. It's kind of argument by contradiction. So anyway, one of these, as long as it's some kind of time-dependent behavior, not a fixed point, one of the exponents has to be 0. And then if the attractor is chaotic, then we need some degree of instability. So one of them has to be positive. Okay, so now we have these various things we're looking at. Attractors, dissipation rate has to be positive, means at least one exponent has to be negative. If it's a flow with a dynamic behavior, one of them has to be 0, and if it's chaotic, one of them's got to be greater than 0. Okay, so now we can actually start looking in higher dimensions. So here's the classification scheme from 1-dimensional flows up to 4-dimensional. Remember before, the 4-dimensional ones I didn't know about, but now I can start to tell you what's sort of new here, and it gives us a little bit of insight as to what's going on. So remember, 1 dimension, all we had were fixed points, and those, as in varying sets, there's only one kind that's stable, stable fixed point, and its Lyapunov spectrum has one exponent, and that's got to be negative because it's an attractor. The dissipation rate has to be negative. Okay. 2 dimensions, well, fixed points, but now we have 2 dimensions. Both perturbations away from the fixed point are exponentially damped, therefore both exponents are negative. We have this new behavior in 2 dimensions, the limit cycle. Well, it's stable, therefore I need at least one of these to be negative, and it's a flow, it's time dependent by the argument I just gave you. The other exponent has to be 0. Okay, same thing in 3 dimensions. Fixed point is stable in all 3 directions, therefore the corresponding Lyapunov exponents have to be negative. We have a limit cycle. Now we have 2 negative exponents and then 1 0 exponent along the direction of the limit cycle. Okay. Now the torus comes in. It has 1 negative exponent being an attractor, but the signature has 2 0 exponents. Why? Well, one of them has to be 0 because it's a flow. So the differences along the trajectory don't grow or shrink on average. Then the other one is on the surface of the donut now that we're imagining. Perturbations don't damp or grow. If I just perturb the orbit just a little bit, then those two now neighboring trajectories are just going to follow each other around. It's a direction of neutral stability, and that has a fill out the surface of the torus. And then chaotic attractor, like the Russell and Lorentz, negative exponent and large one, because it's the attractor. Exponent associated with the direction of flow is 0, and then we have the positive exponent. So this is why you have to go to 3 dimensions in flows to see chaotic attractor. This constraint I just gave you means the first time you get to have a +0 minus signature, or might have a plus exponent. Okay, so that's all familiar. That's just a summary. Now, what about 4 dimensions? Well, let me not take anything in lower dimension can be here. I'll just show you what's new. So this is one of the uses of this. We can now start to imagine, perhaps in a slightly formal way, what these new kinds of behavior could be in 4 dimensions. Well, we can have limit cycles and a torus. We can also have a 3 torus. That is, again, a large negative exponent, and then 3 neutral directions. Well, one along the direction of the trajectory, and then 2 neutral ones. So this is filling out some sort of solid 3 torus in 4 dimensions. I have difficulty imagining what it is, but I can work with this. This I can interpret. So these things exist. Chaotic 2 torus. Okay, so this looks like the torus up here, except I've got it on a positive exponent. So now I've got some sort of donut surface, and there's yet another direction in which things are exponentially separating and unstable. Again, somewhat challenged to visualize an example of this. You can do this in these cases. If you have a 4-dimensional system you're interested in, like that Russell hyperchaos system that's in the Favorite Flows lab. You can take cross-sections through the 4-dimensional space to see a 3-dimensional object. And you can actually convince yourself that well, actually, it's this. So the final one, sort of new kind of chaos, is, again, we have to have a large negative exponent, 0 exponent along the flow, and then we have 2 positive exponents. So again, what does that mean? That means in the 4-dimensional neighboring space, there are going to be 2 directions in which I'm getting exponential amplification. So the hyperchaos 4-dimensional flow in that lab is this guy. And you can take cross-sections through the data and sort of convince yourself that it actually has. Also higher dimension, remember, the fractal dimension depends on the number of positive exponents before you sum to get negative. So this guy will look 3-dimensional plus some fraction, depending upon how strong that negative exponent is. Okay, and so on. I mean, you can just sort of work this out. There's actually a systematic classification scheme that now gives us at least some, again, it's just based on a few numbers, but it does let us now imagine in any dimension what kinds of behavior that can be. You know, stable and attracting chaotic behavior or quasi-periodic behavior. A particular application might have more detailed questions, but this is a nice start. And if you're looking at a turbulent fluid, well, a turbulent fluid is an infinite dimensional system because each volume element is its own little dynamical system. So over a 3-dimensional domain, I have an infinite number of degrees of freedom there. Well, but it's also dissipated. When you pump energy in, the thing heats up and so on. So people have been interested in, if you looked at various turbulent flows, in principle, infinite dimension, but you can show that the system contracts down into something that can actually measure this dissipation rate, D. But what dimension is it? So people, depending upon the parameters in the flow, what kind of flow you have, convective instabilities, Couette-Taylor, all sorts of different kinds of forms of sort of weak turbulence, and people tried to estimate this, sometimes getting dozens of dimensions or hundreds of dimensions, not infinite. So again, I'm not really interested in, what's that?
10 to the 23.
Well, yeah, that's called statistically homogeneous turbulence, where basically every molecule is doing its own thing, as if it was like an ideal gas, or something like that, yeah. But below that regime are all these very, very structured flows. In fact, if you go into the hydrodynamics literature, this is very flowery language about wavy, double scroll vortices, and trying to capture some of the regularity that the experimentalists are seeing in the flow configurations. Now, using this, you can go in principle, and measure a little more quantitative. How many active degrees of freedom are there? How unstable is the flow, and so on. So it's quite useful, both formally to get some idea of what can happen classifying behavior. Again, we're not solving any particular equation to conclude this. The topological structure of dynamical systems lets us actually think at this higher qualitative level and get this kind of classification state. Okay, so finally, what is a chaotic attractor? I mean, we've been looking at these things. One-dimensional maps, two-dimensional maps, flows, and so on, three-dimensional flows. So just to kind of go through, maybe at this point it's fairly obvious, but I think it's helpful to be precise at some point about this. What up to this point has been a little bit kind of informal use of, intuitive use of the language. Okay, so we want to know what a chaotic attractor is. Well, the first thing is it's an attractor. If you remember, that subset of the state space, that's an invariant set that the flow takes back into itself. You start in the set, it comes back to itself. In addition, to be stable or attracting, there has to be some subset of the state space that contains the attractors. Let's think of it. Here's our invariant set that kind of puff up. There's kind of a neighborhood or vicinity of the invariant set. Call that U. And then under the flow, that set gets sucked back onto the invariant set. And then kind of legalese also should be this set lambda that I'm trying to characterize as an attractor. It should be minimal. There's no proper subset of lambda that has both of those properties. In other words, up to this point, if I had two attractors, I would consider the union of them an attractor in that definition. So this is what the minimality is doing. We just want to focus on one of those. There's no way to decompose it into a separate little attractor. Okay, but now we're talking about this complicated set of orbits and trajectories, aperiodic long-term behavior. So now we have two ways of adding on a criteria to talk about mechanics. One is that there's at least one Lyapunov exponent on the invariant set that's positive, or the other is that this metric entropy, Kolmogorov-Sinai entropy, is positive. So that would be it. So it's a stable invariant set with instability measured by the Lyapunov exponent or the entropy rate. So when someone says chaos, this is what they should mean. Okay, so that sort of finishes up discussion of chaos. Now what I want to do for